Kia ora koutou katoa, e hui tahi nei tēnei rā. Greetings, thank you for joining today's webinar. Apologies for the slightly delayed start. We've had some issues with some of the links. Some of you may have joined as a participant. We'll keep you on mute, but otherwise everything should be working. Pleasure to welcome you today to this science webinar. We've had a lot of interest, very topical subject. We'll be hearing from Andy and Bill shortly. Topic of next generation earthquake and tsunami hazard and response. Professor Andy Nicol will go first from the University of Canterbury, Dr. Bill Fry from GNS Science. Together, Andy and Bill lead the earthquakes and tsunami program for the Resilience to Nature's Challenges Earthquake and Tsunami program. So the way the session will start, Andy will be talking about aspects of the work that the team has been doing in relation to the new earthquake simulator model. He'll be comparing it to the record of historic earthquakes and give some examples of how that might help us understand the earthquake process. And then Bill will be talking about examples of different applications of the new models for improving resilience. So Bill and Andy will speak for about 40 minutes or so, and we're hoping to have about 15 minutes at the end for questions. There's a Q&A function in the meeting, and you can use this at any time and upvote any that you see that you were going to ask that you'd like to see answered. And also keep an eye on that window for links that we'll post to any resources that are mentioned, including a feedback survey at the end of the session. We are recording today's session and we'll send out a link to our YouTube channel for that when it's ready to your email address. So I'll hand over now to our first presenter, Professor Andy Nicol. Thanks, Andy. You're on mute, Andy.
Is that better? Can anyone hear me?
Yep, that's great, Andy. Thanks.
Right. I will. And can you see my screen?
Yes, if you just want to click on presentation.
Yep, I'm not 100% sure why my system keeps turning me off. Maybe there's a sign there. Okay, so today I want to talk a little bit about the earthquake simulator research that we've been doing. I'm going to talk a little bit about the rationale for why we want to generate virtual earthquakes. I'll talk a little bit about the model, and then I'm going to dip into some of the things that we've been looking at in the model. And I'm going to talk today briefly about earthquake and fault interactions. And the main reason I'm going to do that is because almost always the first question I get asked about earthquakes is what's going to happen next? More explicitly, when's the next big one coming? And this area of research offers us some opportunity to start thinking about, or at least looking into what the future holds for us regarding earthquakes. I'm talking here, but I'm really talking on behalf of a large team from quite a range of organisations. So please bear that in mind as I move along. Okay, so the rationale for using the earthquake simulators really revolves around the earthquake information problem. Essentially, to summarize that, to get information about seismic hazards, we need to have earthquakes to work with. And the problem is that if we can either use historical earthquakes, so in New Zealand, those are earthquakes that have happened over the last 180 years. And in that case, if we look at those historical earthquakes, we have roughly about 20 that are greater than magnitude 7 and close to land. If we think about, we can also use prehistoric earthquake information, and we have information on roughly 200 to 300 prehistorical earthquakes. If we think about that information and how much how much it represents in terms of the total number of faults we're looking at. In the current community fault model, or the fault model we use or we will use for the earthquake simulator, we have about 900 faults. We've got information on around about 50 of those faults. So only a few percent, 5% of the faults we actually have any information on. So if we can compare that to the number of earthquakes we might have experienced, New Zealand might have experienced over the last million years, that number's in the hundreds of thousands. So we have a situation where we have a short time period for the historical record with very few earthquakes to use to figure out what might happen next. And in the prehistorical record, we have a few more earthquakes, but we only have a small representation of what's there. So we have to somehow get around this, this information deficit problem. So to do that, we could employ a number of different avenues of research. We could continue as we've been doing and doing reasonably successfully. We could continue to collect more information, so we could wait a bit longer for the historical record, or we could go out and look at active faults and get more information on prehistoric earthquakes. The problem is that the numbers of faults that we have prehistoric earthquakes for, that number I gave you of roughly 5% of the total population of faults, we've collected that over the last 30 or 40 years. So to roughly double that number, even if we were really efficient, maybe add a little more, that would still take us another 30 or 40 years. And at that point, we still would only have information on possibly 10% of the fault population. So what we've decided to do is to rather than look at the information itself, to generate our own earthquakes. So to generate a physics-based model that produces virtual earthquakes inside the computer. And what that will do is it'll enable us to access reasonably quickly information on the earthquakes, and we're hoping that it'll help us forecast a range of earthquake hazards in the near future. So what is an earthquake simulator? Just very briefly, the earthquake simulator is actually a physics-based model which is run inside a computer, and it approximates earthquake processes. I say approximates because we need to, in order to make the model run and to run fast enough to be useful, we need to have a number of approximations for the physics that's actually going on. So we have this model. We have to input known active faults, and the map on the left of your screen there shows the known active faults that we are currently working on. So as of 2020, so that those faults, we have information on the location, the size, and the slip rate. In addition to that, we have information on the rock and fault properties. We use that in the model, and essentially what we do is we take the model and we stress the faults, or we load the faults, and then we track the earthquakes that result from that stressing process. And the upside of all of this is that we can in this particular model is we can use hundreds and hundreds of faults, and we can generate earthquakes over millions of years. And over that period of time, we at least in the model space, we have a complete record of all the earthquakes. And that in itself is quite useful. So we can have hundreds and hundreds of thousands of earthquakes in the model, and that really puts us in the space where we can start to think about looking at the statistics of the earthquake process and the probabilities of certain events happening. So for our purposes, we're using software called RSQ Sim. It's previously published software, and we've essentially applied that software to New Zealand. So currently we actually have a virtual earthquake model running for New Zealand. So throughout the rest of this talk, if you see Shaw et al. Preprint, that refers to the model that we currently have running for New Zealand. In this particular model, what we decided to do was to take the active faults or the earthquake sources from a previous publication, this Sterling et al. Publication from 2012. So we had kind of a base situation to compare our results to and to compare the resulting hazards to. We have subsequently re-looked at the active faults, so the community fault model, and we've increased the size of the number of active faults in our database from about 500 to over 900. So a significant increase, but we're not going to be talking about those today. One of the big things about the model is it's all very well to generate all these earthquakes, but we need to have some certainty that the earthquakes in the model are actually reflecting in some way or have some similarities to what actually happens in nature. So part of the process we've been going through is essentially comparing the earthquakes, not individual earthquakes, but in general the earthquake populations, comparing what we have in the model to what we actually are able to observe. And so here we have just got a couple of maps on the left hand side here. These are the historical earthquakes over an 80-year period, and on the right hand side is just one 80-year snapshot from the model itself. In general, they bear some similarities. There's a few differences around the edges up here and down here because our model doesn't extend that far. But in the main, most of our events are tracking through the central part of New Zealand, both in the model and in the observed historical period. So there's a general accordance. One thing that I would point out here is that in this particular 80-year period, we do have an event on the Alpine Fault, quite a large event, which of course we haven't seen in the historical record. So what I want to do now is just very briefly go through two examples two examples from our historical earthquake record, which we've looked through the model catalogue to see if we can actually see any examples which are similar to those. The reason being that if we can start seeing events in the model catalogue that look similar to events we've had now, we can start thinking about the question of what is going to happen next. So the first example here is from the Kaikoura earthquake. So in the map here, I've just shown in red the surface ruptures from the earthquake. As the majority of you will know, this particular earthquake was somewhat of a surprise. The expectation that we would see an earthquake that ruptured this many faults was essentially not there. And so one of the things about this particular event is that we were surprised to see it. And the question is, okay, if we had the model in 2015, for example, would we have been as surprised as we were when the earthquake actually happened? In other words, can we actually see events like the Kaikoura event in the virtual earthquake model? Actually, before I move on to the next slide, I'll just point out that these faults here, the red lines, they're the faults that ruptured the ground surface. We also think that the subduction thrust, which comes under Marlborough in this direction here, dips under Marlborough, that also ruptured in the earthquake, and you can kind of see that in these schematic diagrams on the top left. So if we look to our model examples, so here's an example here. This is a magnitude roughly 8.4 earthquake. It's in the Wellington region. You can see the coastline here. This is event, just to give you a hint of sorry, how many events there are in the catalogue. This is event 1 million or something close to it. And in this particular case, what we're showing here is the subduction interface, and that ruptured during this event. The colors tell us about the slip on the subduction interface, and all these blue lines here are faults in the upper plate, which also ruptured along with the subduction interface. So in this particular case, what you can actually see is the subduction interface slipped with up to about 14 meters of slip underneath the Wellington area. And the Wellington fault and parts of the Wairarapa fault also broke during the same earthquake. And this is not an isolated occurrence. We've gone through the catalogue, and there are many examples in the virtual earthquake catalogue that have features which resemble what we saw in Kaikoura, and which provide us at least indications that this is not an isolated event, and provide us a way in of actually assessing what factors actually contribute to the development of Kaikoura type events, and what we might expect to see next. So lastly, I just want to talk a little bit about earthquake triggering. It's a very common phenomena. The reason, again, for talking about earthquake triggering is that if we have an earthquake, if we understand the triggering process a bit better, then we can start to think about what might happen next. So on the left-hand side here, we can see this is a map of New Zealand, and I've just identified some events here which happened in close proximity to each other. So there's the 2010 and 2011 earthquakes. Over here we have the 1929 and 1968 earthquakes very close to each other. So the close proximity of these earthquakes and the relative close proximity in time suggests that one may have been triggered by the other. Here's an example from this box in here. So this is this red line here is the 1888 earthquake on the Hope Fault, and right nearby the Poulter Fault, which ruptured in 1929. You can see in this case, at least in geological terms, the events are very closely spaced in time, and geographically they're also closely spaced in time. So the suggestion is that the 1888 event may have changed the stress conditions, which essentially resulted in the triggering of the 1929 event. So do we see this in the model? The answer to that is yes. There are lots of examples of triggered slip events. So in this particular plot here, we've plotted time on the vertical axis and latitude on the horizontal axis. You can see these bands running up through the model here. They're essentially telling us that over this period of time, which is about 1500 years, we're seeing many of the earthquakes being located in the same sorts of areas. Just as a reference, Stewart Island down here and Auckland over here. The thing I want to focus on here are these horizontal lines. So wherever you see a horizontal line across the model, essentially the events are very closely spaced in time. And you can see from their latitudes, they're also closely spaced in location as well. And these are almost certainly cases where there's some form of triggering going on in the model. And we can look at that in a little more detail. So here's an example again from Wellington. I don't mean to be picking on the Wellington region. These were just some lovely examples. So in this case here, this fault here ruptured at time 0. The epicenter's here, and it was roughly a magnitude 6.9. And about 4.5 months later, we had this event here, which ruptured nearby. And the suggestion here from looking at the stress redistribution from this event is that this one was triggered by the first event. So the key here is that we can actually see the triggering process inside the model. We have an understanding of the stresses involved and the properties of the faults involved, and we can start to look at under what circumstances we would expect to see this triggering, which will help us understand better what's going to happen in the future the next time we have a big earthquake and we want to know, well, what happens next. So if I could just quickly summarize what I've said. So we have a simulator working for New Zealand at the moment. It shares many similarities with both historical and prehistorical earthquakes. We can see in the simulator that it's producing some of the features that we can recognize from the historical events. So it's reproducing events that look a bit like the Kaikoura earthquake. It's reproducing earthquake triggering. And it allows that in itself allows us to dig a bit deeper into what processes are going on that produce these multi-fault ruptures and earthquake triggering processes. So what I'm going to do now is, so that's my talk finished. I'm going to hand over to Bill now, who is going to talk about some of the applications of the model itself, and hopefully we can all see Bill's screen now.
Great, is that working for everyone? Can you see a title slide? Awesome, thank you very much, Andy. That I think was a very useful introduction to the model. And once we do have that concept of a million-year earthquake record, your brain just starts to work and you start to realize the possibilities of all the multitudes of things you can do with such a model. And we're really in the early stage of even thinking about a lot of the downstream applications. So what I'm going to do for the next 15 or 20 minutes is I'm going to give you a broad swath of some of the things that might be possible, and then also hone in on a couple of of key downstream products that we've started diving into already, and I'll show you some preliminary results of those. When you are able to generate what you think is the full spectrum of seismic behavior, then you can really take a step back and think, well, for our next generation of hazard models, can we use a physics-based or a deterministic method to define hazards? So rather than traditional statistical approaches that have some limitations from observations, if we can overcome the significant challenges of imposing physics on these models, then we can well imagine that we can come to these two, what I call big fish. And I say think blue whales, so about 30 meter whales, you know, really big sorts of creatures. So that the obvious two holy grail outputs of the simulated catalog are next generation physics-based hazard models and next generation local source tsunami hazard models. So when we look at both of these large topics, we understand that what we're doing now is we're laying the groundwork for that next generation. It's going to take a lot of work still to get there, but we believe that this is where the global community is going, and we believe we're going to provide a pathway to get there in New Zealand. Then if you take another step back and you think about medium fish, let's think of the Aotearoa, which are about 20 meters long, so still a substantial product, a substantial delivery from the catalog. You might think of testing early warning algorithms. So if we have existing tools to warn us of impacts of events before they happen, how do these tools work on this very large catalog? So statistically, are they capturing most of what we see in reality? One thing I quite commonly like to tongue-in-cheek say is that nearly every large event we've had over the past decade, we've seen it happen and we've said, wow, we weren't expecting that. We learned so much after the fact. I don't want to learn so much after the next big event, and I don't want to learn so much because I want to think that we've seen the range of Earth behavior and we'll already be expecting some of those things that previously we wouldn't have expected. We can also use this sort of catalog to improve estimations of ground motion. So perhaps think of a situation in which you have a hill that's oriented one direction, you have a whole bunch of earthquakes that are happening to the east of that hill with a particular direction of shaking. Then you might imagine that that hill is going to amplify ground motions with a particular bias in a particular way. So we're trying to understand statistically from the model if we can predict that sort of behavior. We'd also like to, and this is a rather new novel application of the model, see if we can use this sort of model to understand post-seismic, co-seismic, or post-seismic changes in secondary hazards. For example, after a big earthquake, do we get changes in groundwater? On the right-hand side is a conceptual model of how I see this work fitting in the greater hazard and response workflow we have. When I think of a hazard, I think in three main blocks. I think pre-event, and this pre-event is really a resilience building phase. And then I think of the hazard itself and the response, and then the recovery phase on after that. So if you imagine this bubble of RNC2 earthquake cycle simulator, I think that creating this catalog underpins not only the preparatory phase, that phase where you're building resilience by doing things like making next generation hazard models, but you're also feeding in to these other work streams that develop ways we respond and ways we recover. We currently have another large research program that's developing these response tools. It's an MD Endeavor program, and we've developed the two work streams very much co-aligned so that we can ingest information from the simulator to define the problems we want to solve in response. So we don't want surprises when the next big earthquake happens. And we want to use the earthquake simulator catalog to test the solutions we develop here, all to deliver the next generation event science response. Okay, so I'm going to focus on these two topics just to show you two examples of downstream products. One is tsunami early warning, especially with light of in light of the new government New Zealand tsunami meter array initiative. and the other is looking at coseismic changes to groundwater. So if we want to think about the tsunami early warning problem, we need to take a step back and we need to think about what we're actually trying to solve. So when a tsunami happens or when a big earthquake happens, the first thing we do is we use a seismic solution, so think beach balls and earthquake magnitudes, as a proxy to let us try to guess what the tsunami generation would be from that earthquake. So this information just about the earthquake really isn't sufficient to unambiguously define a tsunami source, and I'll tell you why that is in this slide. I'm sure we're all familiar with this concept of beach balls. This was an earthquake that happened a couple of years ago now, just north of New Zealand. But what a beach ball does is it shows you a pair of conjugate planes. So each of these beach balls shows you two possible fault planes that could have given rise to an earthquake. You might think of that in this second panel here, where you have one conjugate plane here and a second conjugate plane here. So that comes from one of these beach balls. On the right-hand side, I'm showing you just from two different beach balls what we might get from each of the four planes that the two beach balls would define. And we might get different beach balls because we're using different data to solve for the earthquake solution or different parameters for the solution. So each beach ball gives us a pair of possible tsunamis that would be generated by tsunami forecasts. So just from two of these, you might think of a situation here where you have four different scenarios, and each of these scenarios are quite different, and they have different impacts in New Zealand. Overlaying on top of that are stars at the locations of our installed and planned New Zealand DART array. So the idea is that we can use the RNC2 catalog to see if we develop early warning mechanisms based on this array, how much of the event space, how many of the events that happen in the future are we going to provide useful warning for? So to do that, I'm showing you one example of a large event from the simulation. This is example 32,060. It's a magnitude 9.1 earthquake. And you see the background subduction zone in the large patches here, but you also see a lot of the shallower crustal faults that failed coseismically. So these were faults that when the large subduction zone thrust fault failed in a big earthquake, they were triggered simultaneously. Andy's already talked about clustering or about earthquake triggering and fault interaction. So this is a case where you get a lot of these upper plate faults failing. On the right-hand side is a vertical deformation model. So if you take this distribution, or the amount that the land has actually moved, you can turn it into an approximation of how much the ground surface moved up or down. So that's what I'm showing you here. After this big earthquake, the ground in red was elevated, was uplifted, the ground in blue subsided or downdropped. And then you can turn that into a tsunami simulation, or you can forecast or predict the tsunami that would be generated by this sort of uplift. And that's what you're seeing in this big panel down here. So for every event in the catalog, we can calculate some sort of tsunami coming from that, and we can look in relatively fine detail with a few caveats. So once you have that simulated wave field, then you can predict the wave that you would actually measure at the tsunamometer network in black here, and then you can, and this is at 3 different tsunamometers, DART B, DART C, DART A, and then you can fit that in an inversion procedure. So the red is a fitted tsunami measurement. So the idea is that in the next big tsunami, we have measurements like the black, and then we fit them with measurements like the red until we get an idea about the tsunami source. So what created that tsunami, and then we can make forecasts for all of our coastal New Zealand zones. In green is a comparison with what we would get for a tsunami prediction purely from the seismic information alone. So once you have that, as I was saying, once you have the inversion and you fit the data, you get something like this that looks like a slip distribution. All right, apologies, am I back? Yep, and do you have my, my presentation? All right, so now let's imagine we can do that 10,000 times. Then we can start to develop a statistical understanding about how well process for future earthquakes. All right, let's change gears now and look at an example for changes in the water table. This is for another event in the catalog, event 588. Again, this is when we calculate the relative surface displacement owing to this earthquake and the triggered crustal faults. So uplift up to 10 meters in red colors and subsidence down to 10 meters. You see the effects of some shallow crustal faults up here. And then you can look and you can see what's the change to the water table. So this is the change to the head of the water table. And this is, if you look at the difference between the head and the topography, you see a relative rise of the water table. So positive values mean that after this earthquake, you might expect a shallower depth to the water table, and brown colors might be a deeper depth to the water table. So this is a zoom in of the southern North Island region, again to pick on Wellington, as Andy's done. So in places where you see green, that's places that after the big earthquake, water is closer to the land surface, and you might have possible follow-on hazards of that, like inundation through flooding, higher tendency to flooding, things like this. Or you see areas in brown where you have a deeper depth to the water, so you might get things like dry wells or reduced hydrographic flow. You can also, using a model of how water flows, groundwater flows, you can start to quantify because of the differential uplift, because of think of the tilt owed to these models. You can imagine a change in that flow. So on the left-hand panel is a change in east-west flux. So the change in the east-west flow, where positive values, green values indicate a flow to the west or greater flow to the west, and brown values indicate either a reduced flow to the west or greater flow to the east. And you can do the same thing for north-south water flow. And I'm going to zoom in to the southern North Island again, just to show you the sort of scale you might think about having effects on. So you see there's a lot of information that's not just captured in the deformation model, but also requires high resolution groundwater modeling for. But the implications in a response mode, or even trying to understand the probabilistic risk you might face from something like that, are that these changes in groundwater flow might affect things like contaminant arrival times, if you think about a contaminant flowing in the groundwater, or perhaps drawdown at wells through pumping. This is a blow-up of Hawke's Bay, showing you some changes around the Hastings area. It's the same thing as the previous slide, and I'm going to pass through that. But you get the idea, and I think your brains will start to think about being able to statistically forecast the likelihood of this in a hazard model type term. Now we're going to talk about surface water flow. Imagine this is a very large watershed where the water feeds some sort of stream or river, and the river being shown by these high values of this. So this value is just a measure of the essentially the surface or the number of pixels in the model that feed into a particular point. So rivers drain through this yellow sort of area. If you take that concept and you say after the surface deformation of the particular event, how do these waterways change? Then you can calculate the difference, either the positive or the negative difference of the number of pixels feeding into these different waterways. So places in red are places that we would see after the event water wanting to go to, so rivers and streams wanting to go to, and places in blue are places we would see the rivers wanting to evacuate or to migrate away from. And this, of course, has other downstream implications, including stresses on levees or undercutting of infrastructure or increased flooding hazards. And there's an example again from Napier Hawke's Bay. So places where the drainage might previously been in this direction, and then after the event, you see a small shift in direction. So these maps, the resolution of these maps is dependent on the resolution of the input models for it. So you can well imagine we could go to higher and higher resolution if we needed. There's an example from the Capri Coast just showing the same sort of thing. I'll rush through those last couple of slides because I want to show you bonus material right now. So let's think about what happened last Friday. What happened last Friday was very challenging from a tsunami modeling perspective because we had a superposition of the tsunamis from the three events. So you might well imagine that from the original event we had, the East Cape event, we had tsunami energy that was trapped for a long time. I think 12, 24 hours after this earthquake happened. And then you superimposed waves that were generated later in the day from these events, especially the 8.1 event. And when those waves from the 8.1 event came into the harbors, we were adding energy. So the residual energy from the first event and then the energy from the second two events were adding up to create a very challenging forecasting condition in a lot of our harbors. So the question is, how often does this happen? How often, when we're going to be responding to tsunamis, will we need to worry about having multiple tsunamis superimposing? And that's another great thing about the RNC2 model is we can start to query and look through the model and say, well, how often do you get to events that are happening within 2 tsunamigenic events that are happening within 12 hours of each other, for example? So I'll summarize there, being mindful of leaving plenty of time for questions. So we think that the model is allowing us to capture the stochastic range or the spectrum of possible earthquakes. And we think that that's going to open up a huge potential for improving resilience. And I very much hope you see strong outcomes from this change in thinking to physics-based models over the next few years in the areas of seismic and tsunami hazards, testing of early warning algorithms, understanding earthquake clustering, things like we've had in New Zealand over the last decade, and we'll have better models of co-seismic impacts of big events. Thank you.
Great, thanks Bill and Andy. That's a tour de force through some really exciting early outputs from the earthquake and tsunami program, from the resilience challenge, and with really exciting potential to address some long-standing issues for us across a range of hazards. So questions are coming in, and if you're still thinking about yours, there's plenty of time to pop those into the Q&A, but I'll just start off with the ones that are there now. So Mark was asking a question about fault model improvements, and I guess the potential to reflect those in the active fault database. I guess that's a question for Andy. You might still be on mute there, Andy.
Some people just never learn. I presume that the question revolves around the fact that we are constantly updating the fault source model. So the active faults database is being updated. As I mentioned in my talk, there's a fairly dramatic update coming. So the next version of our simulator will hopefully include that. And there's provision to include at least one more update after that. So the idea is to keep improving our fault source model as we can, and hopefully that will keep refining the kind of results we get out the other end.
Can I add a comment to that?
Absolutely, go for it, Bill.
I presume that's Mark Sterling, I guess. But one thing I hope comes out of the model is an understanding of seismogenic depth and the depth to the base of faults in a dynamic context. So the idea that smaller events might have shallower seismogenic depths than larger events, I think is a very a very useful one, and that's definitely something that I could imagine exploring, and that might feed back into a fault model, especially the places in the fault model where we have the least information, which are those at depth.
Great, thanks guys. The next question is from Cliff Gibson from the Waikato Regional Council. What's the time frame on the next generation hazard modelling?
This is seismic
Andy.
hazard, is it?
Yes, I assume so. Yep.
Yeah, so can I just emphasise two things around that? So there is, running in parallel with our RNC2 program, the National Seismic Hazard Model is also going through a fairly substantial update, and that update is due for completion, I think, middle of next year. The second comment I'd make is that at the moment, I guess the work that is being done in RNC2 is not explicitly included in that update. They've got enough to do without adding this new information. But Bill and I are hoping that as the simulator project develops, that in the future updates we'll be able to include our results, and that will help refine the seismic hazard models more.
Great, thanks Andy. Okay, the next question is from Adam. The existing earthquake model has defined boundaries. Does the recent Kermadec subduction earthquake have relevance for onshore earthquake triggering and stress changes? Probably for you, Bill.
All right. Yeah. Sure it does. We know that stress distributions and certainly the dynamic effects of stressing from the earthquakes can happen at very long distances. Right now, our simulator, we have essentially two different simulator catalogs. One is the one that Andy presented, and that's what I think is a relatively good first stage catalog. And we have really just a prototype test of concept model of the Kermadec.
I can't hear you, Bill.
Yep. Hello. Can you hear me now, Andy? Hey, everyone. Okay, so I was saying we have two different models. Stress is definitely from the Kermadec earthquake effect onshore. The two different models we have are a relatively advanced model of terrestrial New Zealand and a proof of concept, a relatively unadvanced model of the Kermadec. We don't have those two merged together now. The idea is in the future we will merge those two together and we'll extend the simulations to the north.
Great, thanks, Bill. We've got questions coming in thick and fast, which the team will be publishing. So the next question is from Anonymous. Question about permeability and interconnectedness. So how much do you input about local conditions in relation to permeability and interconnectedness of fractures? So in relation to the groundwater, Bill?
That's something I can't answer, apologies, and I would refer the question to Roger Westerhoff or Peter Johnson for a useful, sensible answer. If you send me an email, I'll put you into touch with them. Great,
thanks, Bill. Another anonymous question. What is the time step of the simulation? To identify overlapping tsunami will have to be very short.
Yeah, the way it works is when a single patch triggers. So if you imagine if you imagine a big fault being broken up into smaller patches, each of those patches have a strength. When the stress is acting on one of those small patches overcome, it fails and it redistributes stress. It'll redistribute stress to things in its neighborhood, and if it's that redistribution of stress triggers another one into failure, it'll clump together and be associated as one event. So this process goes and goes and goes until it's we think that that's the end of the dynamic rupture process. And then it's very quickly we can turn around for the next event. So why I told you that is our time discretization is sufficient to capture the dynamic process. and it's sufficient to capture these a 24-hour scale as well. What we don't know is where rate state friction, the frictional laws, in my mind, a bigger uncertainty is where the frictional laws, rather than the computational problem, the frictional laws, we don't know enough about how quickly faults heal, how quickly you get a fluid that's changing the fault strength, and how quickly that change in strength might subside and go back down to a background value. So the physics of it, I think, they're the limiting factor rather than the computational problem.
Great, thanks, Bill. Another technical question for you from David D. Can you speak to the risks of using the uncertain output of a model as input into another uncertain model? So chaining together uncertainties could amplify noise, but how can you check if that's the case?
Yeah, sure, they compound, and that might even be a question for Andy instead of me. So it's a recognized problem, but I think at every point in the process where we can test against either some empirical equation we have that we think represents something about the physical process, it's a useful thing to do just to sanity check ourselves. At the end of the day, we're going to have a model that has a lot of uncertainty, but we hope that captures a lot more of the natural variation in the process than we currently do. Do you want to address that too, Andy?
Yeah, just to say that I really probably didn't. I could have spent the whole time talking about the testing phase of this project. It's really quite critical that we're able to test the outputs from the model against what we actually can see in the real world. And that's a process that's probably going to be ongoing for the remainder of this particular research project.
Great, thanks, Andy and Bill. Next question from John T. How is co-seismic slip parameterized by RSQ Sim? In particular, how does slip evolve in space and time once the event has started?
It's per slip patch. So it involves the total event is the sum of all of the slip patches that have failed. So we get a
We've lost you again, Bill, unfortunately.
I cut off there at the end of the question, hopefully.
Okay, the next question, probably for Andy, from Steve. How often might we expect clusters of M7 plus earthquakes like we saw on Friday? What does the model tell us about that?
As I alluded to in my talk, the model obviously has millions of earthquakes in it, and there are many examples where we have clusters of large magnitude earthquakes. I'm sorry, I can't give you a number on that, but certainly they occur reasonably frequently, at least in geological timescales. I'm not sure, it'd be misleading of me to actually give you a number for on a kind of a human timescale, but they're not as rare as we might have thought. So, and that's something we're going to need to work on in the coming 2 to 3 years.
Thanks, Andy. Next question from Sharon Hornblow from Otago Regional Council. Hi, Sharon. Any thoughts on modelling and early warning systems for inland tsunamis, lake-based, such as Wanaka, Wakatipu, given the short travel times? I guess the utility of the model, Bill, for in relation to inland water bodies.
Richard, I'm sorry, I was offline. I got kicked out. I just got back. Could you please summarize the question?
Sure. So the question's from Sharon from Otago Regional Council about the application of the potential use of the model for inland waterways, lakes, thinking of the southern lakes in particular. Yeah.
And what around that? So I do believe that it would be useful, and I think it's useful from a planning perspective. If you try to, if we try to assign likelihood of a particular lake hazard. So I think it's useful both for freshwater inland and also for freshwater by the coast, where we might think about, say, saltwater incursion or the flow of water near coastal areas.
Great, thanks, Bill. Another one for you from Lick Lefting. How granular is the tsunami model used to measure the wave amplitudes along the coast?
Very granular, but we can take it to pretty high resolution in areas where we have high resolution bathymetry and topography data, so digital elevation models. The ones I showed you are not using high resolution coastal data, so that's you might think about doubling the values I showed you for a coastal run-up, but that can certainly be done.
Great, thanks, Bill. Another technical question, this one from Brian. What is the effect of non-homogeneous crustal structure accumulating strain, the effect on the models?
Yeah, that's a very good question, and one that Andy and I just discussed with Taiwanese colleagues the other day, but from a stress perspective. So the idea is that when we start these models running, the stress field is relatively homogeneous. Through time and through the earthquake process, you get a heterogeneity or heterogeneous distribution of the stresses. So you get a mixing of the stress fields. So I think that's in many ways the same effect as you would have from having geological features, geological heterogeneities that made a heterogeneous stress field. So the idea, and what we hope is the case, and this was really something that I think Russell Robinson pioneered a couple of decades ago, or close to that now, is after the first bedding in period of that model space, then you can think that you have essentially a random seed and you have some sort of initial starting heterogeneous stress field that you can then look at something realistic after that. So we think the homogeneous stresses have a window where they're making us have unrealistic models, and then after model space, after that time, we think it's useful.
Great, thanks, Bill. Yeah, anything from you, Andy, on that one?
Can I just add that obviously with our input faults, so our fault sources, we're cognizant of the fact that we are not capturing all the fault heterogeneities in the crust, and we have the facility to add in, or we add in what we refer to as background earthquakes. So essentially earthquakes happening on faults that we have not explicitly input into the model. And that in itself may, unfortunately, because we don't know the locations of the heterogeneities, that kind of, it has to be to some extent a random seeding process, but we do have the facility to do that, which at least attempts to take some account of those events that we are potentially missing.
Great, thanks, Andy. We've got just a few minutes left. We'll see if we can get through these last three questions. The next one's from Ian Dorr from Wellington Regional Council, Greater Wellington. Did the DART boys on Friday measure anything useful that could be used to inform the tsunami modelling as part of this project?
Not as part of this project, the RNC2 project, but yes, they did measure data, or they measured the tsunami wave, and yes, it was useful information. We used some of the tools that we've been working on under the Endeavour, the NB Endeavour research program, to help us understand what that contributed to our forecasts and pictures.
Great, thanks, Bill. The next question from John Ben from Department of Conservation. If two earthquake events happen close together spatially and temporarily, what distinguishes if they are connected, triggered events, or completely independent? I guess that's for you, Andy.
That's a damn good question. The issue there is it's somewhat of a subjective call in many cases. Unless you actually do independent stress modelling of the events and you can demonstrate that one event actually elevates the stresses in the area of the second event. But in a lot of cases, we don't have that independent modelling. So in the ideal world, we would take the first earthquake, we would model the slip on the earthquake, generate some Coulomb stresses, and then look at that and make some assessment as to whether the change in stress around the second fault was sufficient to change its, or to trigger any activity on it. But I accept in a lot of cases that call is somewhat subjective, and the hope, I guess, is that by using the simulator, we can take some of the subjectivity out of that by understanding the process a little better.
Great, thanks, Andy. I think we'll just better squeeze this last question in from Gareth Davies. Regarding large subduction earthquakes and the resulting tsunami, what are the prospects of evaluating the bias and variability of the Tonga-Kermadec model against historical tsunami events? I guess the question is about whether or not there's enough data and whether you might need to look at other subduction zones.
The first thing I would do is look at the Gareth Davies paper on the probabilistic hazard of that area and see what he has to say about it. I think there are definitely a lot of uncertainties, and it's something we would need to probably be a bit more skeptical than if we looked at a probabilistic hazard model coming out of the terrestrial New Zealand or proximal to New Zealand simulator, mainly because we have a lot more unknowns about the faulting structure and a lot less information from geology about the deformation on faults that we can use to calibrate the model.
Great, thanks, Bill. Well, our time is up. Thanks again to Andy and Bill for the presentations today and the Q&A, and to Nikki and Caitlin in particular behind the scenes for making the webinar possible, and a big ngā mihi nui to all of you for participating. Our apologies if you've had technical difficulties. Thanks for persevering, demonstrating resilience in action. There will be a full recording available shortly, and we'll email out a link to that when it's ready. Stand by for more information from us about our next webinar, but we're looking for something in May and subject to be confirmed. Thanks again. Ka nui tēnei, that's it for now. Kia pai tō rā.